Hello everyone. The menu for today, we will finish the module on congestion control, and if time permits, we will start already the module on BGP. And tomorrow, we will have the usual bi-weekly test. Last week, we saw that the fairness of TCP Reno can be calculated and gives a utility function, which is depending on the round-trip time in a way that decreases with the round-trip time. The question now is, what does it imply? And to understand more concretely, here is a small example, and I'm asking you to take position on who of the two sources, S1 and S2, will get the most. This is a very simple example where I'm assuming the bottleneck is this link, the outgoing link in this direction. We ignore all other possible collisions and packet losses that may occur in the reverse path, for example. So S1 and S2 are sending to this destination, and their throughputs are proportional, are twice the values that are given. The round-trip times are twice the values that are given. So there are, for source 2, 60 plus 10 times 2, that's 140. And for source 1, 20 plus 10, which is 60. Who will get the most throughput? And the correct answer is A. A will get the higher throughput, even though both are competing for the same bottleneck. The only resource that is creating a performance issue here is the capacity of the outgoing link of the router to the final destination. So both are competing for the same bottleneck. For all theories of fairness, they should get the same. They should get the same throughput. So ideally, we should have answer C. But since the utility of TCP Reno is decreasing with the round-trip time, if we think of TCP as maximizing the sum of the utilities of the two, it will give more to this one, because the utility of this one is higher, so you get more mileage, more benefit by increasing it. So that is the fact, which is called the bias of TCP Reno against round-trip times. So we see that two competing sources with different round-trip times are not treated equally. The source with the larger RTT obtains less, which sometimes is thought of being okay, because very often this is confused with another argument that often happens together. When two flows, when two TCP connections have different RTTs, very often it is simply because one is using a larger number of resources. In that case, it is okay to give less to the source that uses more hops. This is exactly what proportional fairness is designed to do. So any utility function will do the same. But the problem is, in the utility function, there is also a bias against the RTT. And as we have seen in the previous example, we had two sources that had exactly the same bottleneck. They were competing against exactly the same bottleneck. So this is an undesired bias. But that's a reality today. It's a problem of TCP Reno and of practically all other versions of congestion control in the internet. The root cause is easy to understand, is we do additive increase, multiplicative decrease. The multiplicative decrease is the same for everyone, for sources S1 and S2, but the additive increase is one packet per round-trip time. In terms of rate, it is smaller if the round-trip time is larger. So that's the root cause. This has an important impact, and it's not fixed today. We will see that there are modifications of TCP that make things a bit less severe, but this is not fixed today. And it means, in particular, this and other reasons, that if you try to download massive amount of information from a server farm, you are in a bad position if you are very, very far away from that server farm. For example, if Microsoft or Google had all of their servers in the US, or in India, because it's much cheaper than in the US, then the performance you would get when accessing them would be very bad, because the round-trip time from Europe to those places would be large. So this is why there is a business that has emerged, which is content distribution networks or local repositories of data, where practically all operators host some server farms that put all the content that is of large volume. So when you download a file from a video inside Switzerland, probably it's coming from Switzerland or from a nearby server that is not too far away. That is one of the reasons, because if you will not do that, then all the people who are watching those videos from very far away would probably get always systematically very bad quality. We can even go one step further and quantify this throughput dependency. There is a formula that is, as we will see, used in a number of opportunities, which is this one. It's called the TCP-Reno loss throughput formula. It says the following: if I have a TCP connection, there should be a link between the frequency with which we receive negative feedback, which in our case of TCP-Reno in standard operation is simply the loss probability. If I lose packets very frequently, I receive a lot of negative feedback. Therefore, the throughput of this connection should be small. If in contrast, I receive very, very infrequent negative feedback, I increase a lot, then I oscillate with large oscillations that are very infrequently interrupted by negative feedback, the throughput should be larger. So if we analyze this oscillation behavior and we do a number of very simplifying assumptions, in particular we ignore all the details of slow start, fast retrans, fast recovery, all those details that are hard to analyze. If we ignore those details and if we assume a very, very long connection, so it will oscillate many times, we can compute the averages. This is done in the lecture notes that I give in addition to the slides, and we find this relationship. The throughput of a connection is equal to a constant, which is square root of 1.5. This has to do with the multiplicative decrease factor, times the packet size. So this is the net throughput counted as seen by TCP. So we ignore the headers of IP, for example, divided by the round trip time and divided by square root of the loss probability. The formula should be understood as this is the throughput you will get if the limiting thing is the additive increase multiplicative decrease phenomenon. So if the network is the limiting thing and gives you a congestion probability Q. If Q is 0, for example, you see that the throughput is infinite, which corresponds to the case where, of course, the throughput that you achieve will not be infinite, but it means the network is not putting any limit on your throughput. This is what will happen if you have a connection that requires a small bit rate, for example, because the server or the source is limiting it, but is using a network that is very, very large. So in that case, you will never receive any negative feedback. So this is a formula that captures a bit more than the utility function that we had before. Again, it's an approximate formula, but it gives us in particular how the throughput depends on the round trip time. We see it's exactly inversely proportional to the round trip time. It's also inversely proportional to 1 over square root of Q, which capture exactly the two phenomena that occur. If a connection has a large round trip time, it will have a small throughput because of this factor. If a connection uses many, many hops, then the loss probability will be compounded by the many hops. If you use 1 hop, you have a loss probability which is that of that hop. If you have 2 hops, the loss probability will be 1 minus the loss probability on each of the hop, which will be, if it's small, roughly equal to 2 times the loss probability on each hop. So if a connection uses many hops, its Q is going to be larger, which will give it a bit less also, as predicted by proportional fairness or utility fairness in general. So let's continue with the example we saw a minute ago, and let's be a bit more mathematical. What will be the ratio? Is it possible to say something about the ratio of those two sources here. And the correct answer is C. To see why, well, it's a small exercise in proportionality. If there are only those two connections, which I'm assuming here, TCP implements a form of utility maximization, fairness, which is utility maximizing, so it will be Pareto efficient. Now, the bottleneck is this link here, so the throughput the sum of the throughput will be 1 megabit per second. Which we, by the way, we don't know. We don't need. We were simply asking what is the ratio. Then the ratio will be that it's inversely proportional to the throughput, to the round trip time, so inversely proportional to 7 and 3, which gives this ratio here. So theta 1 will be more than twice the value of theta 2, which is what we found here by doing some mininet simulations. So we have seen, with some amount of details, TCP Reno, which is the first historical version of congestion control in the internet, which still serves as an important landmark today and is a reference implementation that many systems refer to, as we will see. Now, as it stands, TCP Reno has a number of drawbacks. Could you imagine some? If you would like to fix it, what would you like to fix in TCP Reno? Well, one thing I would like to fix is certainly the fairness issue. We would like to remove the bias against long round trip time. But there is a whole catalog of things that have been discussed and found since TCP Reno has been developed about 20 years ago. The RTT bias, that's what we discussed. It's not nice if you're very far away, like New Zealand is far away from everybody, so it's very bad for them. So they have a lot of content distribution networks on their island. But there are other things, is that the only way we have found a possibility to control the sources is by forcing losses. If you're transferring a file and you lose something, it's not so nice. If you're displaying a web page and you lose some element in your script, for example, you can't execute the script, so the displaying of the page is blocked. If it's a video, it's less severe because in the meantime, video codecs have become very, very smart and they can adapt to losses by temporarily reducing the resolution. But still, it's not nice for many applications, and there is always a penalty, very often in terms of delay. Eventually, the loss will be repaired, but the latency will be bad. In fact, that's one of the key problems for companies like Google. They would like that when you go to a Google search, then you don't have to wait. So what could happen when you open a page and you start Google search? Well, your connection is probably in slow start. So it will increase very fast, except if there is a loss. If there is a loss during the slow start, we will start again to 0 and send only one packet. So there's a lot of penalty if you need a few packets to complete the first page. So this is why Google has worked very hard to make sure whatever you do is achievable within one packet, for example, when you do a search. So the losses here as negative feedback is not nice in terms of latency. There are more subtle things that have been observed by people who have monitored what happens in the network components. Because TCP doesn't control the rate, but only the window is what we would like, ideally, is to have smooth changes to the rate. But when we increase a window, for example, for some reason, because a loss is repaired, what typically happens if the source has a lot of data to send, then it will send everything it can send. So it will send a burst of data. So sources typically oscillate between being blocked and sending a large number of packets, then being blocked, then send a large number of packets. Why is that not optimal? That's because of queuing theory. The irregularity of the packet arrival means that the congestion probability is larger. It's also known in road traffic. If the cars are very smooth, then you have less traffic jam than if the traffic is very irregular. That's one of the queuing theory formulas. Those of you who will take a queuing theory course, like performance evaluation next semester, or a Markov chain course, will see those things. It's called the Polacek-Kinchin formula. So that has a penalty on the backlogs, the buffers in the internet, which is avoidable. We could send the same amount of data by smoothing it a bit, and everything would be, in fact, with lower latency. Another thing is called the buffer bloat, or the self-inflicted delay that I've already mentioned. If a number of sources are starting more or less at the same time, then what they will do is they will fill all the network buffers. If the network buffers are very large, they will receive no negative feedback. So they will send as much as they can until the buffers are full. Now, if the buffers are very full, and today buffers can be very large, they can be hundreds of gigabytes, then the round-trip time becomes larger. Because if you're a packet that arrives at the end of a buffer that's quasi-full, if it's full, you're dropped, you're dead. But if it's quasi-full, you're just at the end of a very, very long queue. You may have to wait for seconds in this router before being processed. Right? Now, if every router imposes a delay of the order of a second, then the round-trip time becomes very large, and there's no benefit. And it's compounded by the fact that TCP gives poor performance to those that have a large round-trip time. And in particular, if you happen to have interactive short flows, like, for example, a combination like Google has of large flows for video and short flows for searches, then the searches might take a very long time. Those are some of the things that the research community is trying to fix. As we will see, some of them start to be fixed, but there's still some work to do. The thing we will see now is fixing one additional problem, which happens when we have what is called elephants, long, fat networks. And this motivates the development of TCP-cubic, which is the widespread application in Linux servers and in the Linux distributions. So that's the one we use in the lab, and it's very likely the one that servers that you're using when you contact a website is also using, with the exception of Google. This is showing exactly the additive increase, multiplicative decrease phenomenon that happens when you have a very, very long flow. This is how TCP behaves. We see that it oscillates around the value, its steady state value, but the decrease is by 0.5 and the increase is linear. Now, if you have very large rates, like here, assume the available capacity for this TCP connection is 10 gigabit per second. That's probably not what you get when you stream a video over the internet, but it's probably what you get, or what you would like to get, if you run a data center or an information technology company, and you have cloud services, or you're transferring you're doing a backup of a computer, so you move some large amounts of files you would like, and you probably have inside your data center, that kind of performance. Now, we know that TCP Reno increases of 1 MSS per round trip time. Here I'm assuming the round trip time is 0.1 second. Then the number here, the capacity is written in packets. The capacity that is 100,000 packets per, corresponds to a congestion window of 100,000 packets. So if we divide by the round trip time, we will obtain 10 gigabits per second. How much time does it take for TCP Reno to do this oscillation? Well, it takes 50,000 round trip time, so 5,000 seconds, so 1 hour and a half. So this goes on for 1 hour and a half and back, and etc. That is considered inefficient if you could find a way to increase faster instead of getting there, right? Because probably it means if your transfer lasts for an hour or a fraction of an hour, you will never get that throughput. You will increase, then you will stop because the thing is over. But that means you have 10 gigabits per second available, you will never reach it. You will get less than the capacity that you've installed. 10 gigabit per second over the wide area network is a large amount today, will be less tomorrow when optical fiber are deployed everywhere, but is not a large amount in data centers or in IT centers in general. This is the problem that caused a new development called cubic, and this is illustrative of the kind of hacks that have been employed to TCP Reno. We will see a number of others. This is showing the same as before. This is the increase, linear increase. Before, we would hit here the capacity, and this is what we would do. What cubic will do is two things. First, cubic says, well, decreasing by 50% when we detect congestion is a lot. This is, in fact, what creates those large oscillations, is because we decrease by a lot, and therefore the amplitude here is very large. On the other hand, they were not bold enough to say, well, let's reduce by 10% instead of 50%. They reduced by 30%. So the first change, which as you see is not so dramatic, is the multiplicative decrease reduces by 30%. So we multiply the window when we feel a loss by 0.7 instead of by 0.5. That's the first thing. So that happens when we perceive a loss. When TCP detects a loss, the window reduces. So assume before the loss, the window size was this one, this horizontal line, called Wmax in this formula. If we would do TCP Reno, we would reduce by 50%, and we would increase almost linearly. What TCP cubic will do is it will decrease by 30%, so it will be on the blue curve, and then it will increase by this function, where I'm sure you recognize the x cube function, x to the power 3. That's why it's called cubic. So this is a cubic function which is shifted such that the origin is here, which gives this formula here. The increase is such that when t is equal to k, so k is computed such that this is exactly when we reach the value Wmax here, and then it increases in a cubic term here, multiplied by a coefficient that has been set empirically by trying a number of things that I will perhaps mention in a few minutes. So that's the first thing it's doing. Now, what is the implication? Well, the implication is that the cubic increase is in fact not very fast at the beginning, then it will be very fast after. So the motivation is to say, well, we are very cautious, we increase practically the same as Reno until we get the value that Reno would, then we are very cautious because then the derivative is 0 at this point, so we increase very slowly. And then if it happens that the value that we wanted to reach is not Wmax, so if we are in the increase phase, we're still tasting the water to increase, then we will go very fast after this point because a cubic increase after this point will be convex and fast. And that's the idea. That's the subtle idea. Now there's a number of small problems to fix. The additive increase so the first observation is that this increase is completely independent of the round trip time. So I showed before the additive increase slope. Now it depends on what is the round trip time. If the round trip time is larger, then the slope of the additive increase depends on the round trip time because it's one packet per round trip time. So cubic has an increase phase that's independent of the round trip time. For the increase of the window, not for the increase of the rate. So there will still be dependency on the round trip time because we increase the window, not the rate. So that's the first thing to observe. Now, if the round trip time is very small, which is the case here, we see that cubic is a bad idea because by being independent of the round trip time, in this scenario, we increase less fast than Reno. So we find here one of the fundamental principles, if you want, of internet congestion control is that the principles should be what we have seen in the first part of this course, but the practical principles in internet are not those ones. The principles are the reference thing is TCP Reno. We had a problem in 1986. We fixed it by doing additive increase, multiplicative decrease. Therefore, we should stick to that. That's the dogma in the internet. So we want to be always compared to TCP-Reno. So we want that TCP-cubic performs at least as well as TCP-Reno in the case where the round-trip time is very small. So what we will do is we will say that cubic make sure that the window increase is at least as fast as Reno's increase. In other words, cubic will take the max of the blue and the red curve. Right? This is what cubic will do. Except there is a small technical problem. The red curve is for Reno, or is it for something that does additive increase, multiplicative decrease with a multiplicative decrease factor of 0.7. So cubic wants to keep that design and say I multiply when there's a decrease by 0.7, not by 0.5. So to fix the problem, what they did is they computed a hypothetical TCP-Reno. They asked the question, what should be the additive increase? By the way, that's the kind of question that I could ask in a quiz. What is, or in an exam, what should be the additive increase value if we wanted to have a multiplicative decrease by 0.7 instead of 0.5 and obtain the same throughput? Would we be able to answer that? Well, we would need to use the loss throughput formula. If you look at the proof of how the loss throughput formula is derived, we analyze the oscillations. And if you can redo the same derivation and find a generalized loss throughput formula that says what is the loss throughput of a variant of TCP-Reno that has changed the additive increase term, the R, and also has changed the multiplicative decrease factor. You can find a general formula. I skip the details. If you do that, you find that it's completely possible. You should increase by this quantity, which is 0.529, so 50% of MSS per round-trip time. TCP-Reno increases 1 packet per round-trip time, divides by 0.5, divides by 2 when there is a loss. If you want to modify this and obtain the same loss throughput formula, if you multiply by 0.7 when there is a loss, you need to compensate this fact by having a smaller additive increase. You reduce less when there is a loss, so you should increase less. Right? So the authors of TCP-cubic did this computation and they found that. So what they did is they simulate what would be the window increase for this modified TCP-Reno, and they take the max of their own cubic function and this one. And this is what TCP-cubic does. And from that, we can obtain easily a loss throughput formula. The loss throughput formula of TCP-cubic is the max of 2 expressions. This one is the expression we obtain if we would redo the analysis with a cubic increase instead of the linear increase and the reduction by 0.7. So this mathematical thing that I did not describe in detail that leads to the loss throughput formula can also be done with other increase functions, and that gives the blue formula here. The red is the TCP-Reno formula, which is also the formula we have if we have a decrease by 0.7 and an increase by 0.529 MSS per round-trip time. This is plotted on this curve here, on this diagram, where I show on the x-axis in log-log scale the loss probability and the throughput that is obtained. The blue formula gives the blue curve, the red formula gives the red curve, and there is one of these curves for every round-trip time. If the round-trip time increases, the curves go down. So the red curves are if we would do only TCP-Reno. This is in log-log scale, so therefore this is a power law. The throughput is a power multiplication of power of Q. So in log scale, it is linear in log Q. This is why we have a straight line here. And if we look at the value for RTT is 100 millisecond, that's the red curve in the middle. And that's the blue curve that starts here, not very easy to see. This is why I put a thick greenish bluish curve. That is what this formula gives if the RTT is 100 millisecond. we see that if the RTT is very large, like 800 millisecond, the blue, the red is always below the blue, even for a very large value of Q, which means if the RTT is very large, cubic is always in this mode of operation. It will always do its cubic increase, and the throughput will be given by this formula. If the RTT is very small, like 10 millisecond or less, then it depends on the bit rate that's available. For example, for 100 millisecond, we see that for 10 megabit per second and above, we are in this regime. And for smaller values, then we need to go to gigabits. But even for 12.5 megabit per second, if we're at 1 gigabit per second, we're close to having the two here. So in summary, TCP cubic, whose goal was to solve the problem of the slow increase for connections that would be able to have a very, very large throughput, but are slow to increase because the RTT is not very, very small, then it does its job. So TCP cubic connection gets more throughput than TCP Reno, significantly more, right? If we are in this regime here, this is a logarithmic scale, so the importance is huge. When what? When the bit rate and the RTT are both large. That's something we can say. If we would like to be a bit more exact, we would have an ugly formula. It's not exactly the bandwidth delay product because of all the exponents here. It's not the product of the RTT by the theta that matters, but intuitively, when the bandwidth is very large and the delay is very large, cubic will solve the problem here. Also, it means if in other cases, when you have a small bandwidth and reasonable RTT, for example, an RTT of 100 or 200 millisecond, like we typically have across European distribution systems, and a bandwidth of order of 1 megabit per second, then there's no difference between Reno and cubic in that case. This is what justifies also the success of cubic, because people believe there's no difference for many practical cases, but in case I need to do a huge transfer, it will do better. So it's better than to use cubic. So this is taking care of the elephant syndrome. Now let's look at the buffer bloat problem, which has led to a lot of developments and probably is not completely solved in the internet today. This is a figure I borrowed from this paper that is trying to sell an alternative to Reno called BBR. And it's showing, as a function of the window size of one TCP connection, two things. On the green axis is the rate that this connection will achieve. And on the second y-axis, which is red, it is showing the round-trip time that this connection will achieve. And here I'm assuming that this connection is going through a bottleneck that has a capacity, a fixed capacity C here. And assume that we ignore the sharing problem, so this is the capacity that this connection will obtain. The window size is dictated, for example, by the window field of TCP, which has to do with the buffer at the source and the destination. Assume we can vary the window size for this connection. If the window size is very small, then this connection is limited by the window size, not by the network. So the throughput it will get is directly proportional to the window size. As we increase the window size, we increase the throughput, and the throughput will be the window size divided by the RTT. Now, because the window size is very small and everything is very small, the RTT is essentially the propagation and transmission time with very little queuing. Then when the window size reaches the bottleneck link capacity, so there is, as we know in this toy example, we assume a well-known number C, that is the max that this connection can obtain. If we continue to increase the window size, what will happen? Well, first let's observe we don't know what is the bottleneck capacity. It depends on how many other connections are competing, so we don't know exactly that we are here. But what will happen is the following. Since when we increase the window size, we allow TCP to send more, but since the rate at which data can be delivered to the source is dictated by something else, by a bottleneck, the rate of delivery of information, the throughput will not increase. But the window will be much larger. Right? What will happen? Well, there will be lots of packets in the buffers of the network. The buffers of the network will buffer all those packets, assuming the buffers are very large here. Then the buffer will fill. And this will be visible by the fact that the round-trip time will increase, because now packets start to be stored in the buffer because the bottleneck link is not able to deliver those packets. So it will store them as much as it can. Up to a point where it cannot store them anymore because it exceeds its capacity. So then it will start dropping and give a feedback to the source that it should reduce the window. Since the window is very large anyhow, the source will oscillate around its optimal value, and the rate will be, of course, not as nicely regular as here, but will, roughly speaking, be equal to the bottleneck link capacity. As we have seen many times, TCP achieves this water tasting phenomenon. It finds exactly what is the bottleneck, so it will do that here. But what we see here is there will be an increase in round-trip time here. This is where the internet operates today. When there are large buffers, you operate here. When there are small buffers, you may operate anywhere in between. But what this paper is advocating is this is where we should be operating. We should find a mechanism of TCP that operates here. As soon as we reach the bottleneck capacity, it would be nice if we have found a mechanism that allows us to stay there without increasing and get to that point here. We will see how we can reach that. Several mechanisms have been proposed. One of them is ECN. ECN stands for Explicit Congestion Notification. In fact, it's very simple, and what is surprising is that it took such a long time to be proposed to the internet, because this is what was already working when the first TCP congestion collapse occurred. There was another network, there are several other networks, but one of them, the most famous, was DECnet, that had something called the DEC bit, which was a congestion, which was a precursor of explicit congestion notification. What is it? Well, the idea is exactly corresponding to the model we saw when explaining additive increase, multiplicative decrease. When a router sees that its capacity is being approached, it will mark the packets that go through it. Now this, in DECnet, it was done in the network layer header. So it would mark a bit called the congestion bit, the DEC bit. When a receiver receives a packet with a bit marked, it will send negative feedback to the source. How does it send negative feedback? Well, DECnet did not use TCP, but it had something equivalent. In TCP, we can use the acknowledgements. When we send data, typically there are acknowledgements. So in the acknowledgements, we could send the information that the routers have marked that there is congestion. And if we do that in a smart way, then the routers are able to mark the congestion, still buffer the packets, but we will operate here, because as soon as you get in these regions, the routers will sense that there is congestion. They will see that the rate at which I'm receiving data is larger than the rate at which I send it. So I start marking the packets. So if we do that here, the sources will reduce its rate, so it will be operating slightly above the point A instead of point B. That's the idea. So let's look at a small simulation of how this could work. I'm showing a source and a receiver and a router that is congested. The output link here marked in red is congested. With TCP-IP, it works in the following way. First, S sends a packet. I'm showing the IP header and the TCP header. When this router sees that its output link capacity is congested, it will mark this packet in the IP header. So it is one of the fields we have not discussed in the IP header. It will mark it here. If this packet is not lost, it will reach the receiver. The receiver analyzes the IP header and sends a message back in the TCP acknowledgement, where there is another field, And in the TCP acknowledgement, if the acknowledgement is not lost, it will reach the source here, and the source will know that it has received a congestion signal. When a source receives the congestion signal, it does multiplicative decrease. And since it is not a loss, the window can continue, so there is no need to do all the heuristics of fast recovery and all that stuff. It simply decreases the window here by 1/2. This is showing the window size for such a case. Small check on your understanding, which should be what? And the correct answer is C. The window increases linearly or quasi-linearly, depending on how TCP implements the additive increase. So 1 is the phase called congestion avoidance. That's the terminology that TCP-Reno gives to what we do when we do linear increase. Then when we receive a congestion, so ECE stands explicit congestion experienced, then the window is decreased by 0.5 here, then it increases again, then decreases by 0.5, and then increases again. So the second thing here is multiplicative decrease. Here there is no slow start in this illustration here. So that's the theory. In practice, there's a small complication. The complication is the coexistence of ECN and regular TCP and regular routers, which did not exist in the DECnet network. All DECnet routers were implementing the DEC bit. But since TCP decided to use loss as a congestion signal, realized much later that there are many drawbacks. In the meantime, the internet is deployed and everybody is using losses as a congestion indicator. In particular, routers drop packets when they are congested. What happens if you are smart and you use ECN in your server and your client? Well, the answer we will see, we'll do a break and we'll see the answer after the break.